So we're gonna get started here. We gotta move quickly. So last question of free response practice. Oh, like the last part of the 2019 one?
I think that person is asking you like if you can go over that question.
But hold up. When you say last question, are you talking about the?
No, I mean
because I gave y'all 6 questions.
No, part C.
Part C.
Of
Yes.
2019.
That's the plan. Yes.
Oh, okay.
Okay. Yes. Can I get the free response practice, pretty please? Yes. If I find where I put it.
Wait, I wonder who sent that one.
I don't know.
Let me think about it where I put it in a second, because I had a copy for you. Oh wait, is this it?
I am.
Haha! I knew I had a copy of it. Here you go. Yep. And then did we need to do all free response questions in the back of the unit besides? No. You're supposed to do 2019. That was the only one you're supposed to do.
all of
Yes,
them?
sir.
I did.
What?
I thought you said,
Kinsey, did you do all of them?
no, wait,
No. I wanted you to do the 2019 free response question. That was it.
and not the 28 one?
2008 one?
Yes.
No. No, we're doing 2008 in class.
She did all of them.
Well, we can have you do a different one, but we're doing 2008 in class. And I think those are the only questions that got put up on the board. By the way, y'all can erase the chalkboard wall if you ever need to. Okay.
It's gonna take a while.
No, because people just use it and they erase it when they use it. Yes.
When you get a long problem, do you recommend us to underline them or in AP exams, or do you think it's easier to just fast forward than just do that?
I don't understand what the question you're asking is.
Do you recommend us to underline the important explanatory variables or experimental units?
I would just read through the context and then, but now here's the thing, you do what you want. If you want to annotate. However, it's going to be presented digitally these days, not on paper, unfortunately. So, I think that there's a pushback and they might be giving the free response on paper, but I know, no, the pushback is that they're going to give the formula sheets on paper, but and this is dumb, they're going to have you put your responses to the free response on a sheet of paper, but they're going to give you the questions digitally. So you're not going to be able to underline in person.
I think
It'll have to be, but I think there's a highlighter thing on the AP classroom and stuff, so you'll be able to use that. But I'll say this, I don't personally do that. I just read through the context, jump to the question and go from there. But I do know some people do like to annotate, so unfortunately you just can't do that. All right. Does that answer your question though, Ryan? I'll go with the yes. I forgot to update the agenda. Skip through that. Forgot to take out that slide. Okay, so at this point we should have everything from the unit at least somewhat mastered. Hopefully, doesn't seem like we have any questions being asked right now. Hopefully that means we're good to go. I am going to go over, did we finish the scope of inference yesterday on 4.9?
Yeah.
Okay, I thought so, but I just want to make sure. Skipping that. Okay. Let's go over the AP free response question, the 2019 number 2. Okay, so here, I know it's small, but I had to do it to save paper. Here are the actual scoring guidelines. Just doing Queens there. Okay. Here's the actual scoring guidelines that were given with this question. And so we're going to go over different elements of this to help you improve your understanding before the DYU. Okay. So let me pull up the question. Should have put in the slides, but I didn't. All right. Okay, so right here. So researchers are investigating the effectiveness of using a fungus to control the spread of an insect that destroys trees. The researchers will create 4 different concentrations of fungus mixtures. An equal number of the insects will be placed into 20 individual containers. The group of insects in each container will be sprayed with one of the 4 mixtures, and the researchers will record the number of insects that are still alive in each container 1 week after spraying. And so when you look at the rubric, I want you to notice a couple of things. So the way that these rubrics work is that there is a solution, okay? So there's an intensive question, then there's a solution, there's part A. That part A solution is an idealized response. That is not what you have to have, okay? So part A has an idealized response there. If you look on the right side of your paper, it says scoring, okay? So, notice there, and I should just pull this up. Here's the idealized solutions under solution, and then down below it is scoring. And you gotta pay attention to this. And so this is where that E, P, and I comes in, right? Essentially correct if you get these three components, partially correct if you only get two of those three components, incorrect if you don't meet those criteria. So, what were the treatments? Is that the first thing that was asked for?
Yeah.
The four concentrations or mixtures or sprays, you can say any of those things. I believe you could list it out. Yeah, so right here, notice how, so like this is all they say, but they say listing the four treatments satisfies component 1. For some reason, you don't have to include the units. I would always include units because context matters. But if the list did not include all four treatments, component 1 is not satisfied. Okay, so component 1, you had to identify the four concentrations. Now I think experimental units here may have thrown some of us off. Did anybody say that what kind of bug were they?
I just put insects.
It's just insects. Did anyone put the insects as the experimental units? Yeah, that's not correct. Because what is an experimental unit? It is the individual that the treatment is applied to. We didn't individually apply it to the insects. We took a treatment and applied it to the what? The containers. So the 20 containers are the experimental units. And so this is why we're doing this before the DYU. This is why we're doing this before the test. But we need to understand, and that's why I'm using this as a thing to talk about. Experimental units are what the treatments are applied to. Experimental units are what the treatments are applied to. So are the individuals that the treatments are applied to. So hopefully that improves understanding there. Okay? And so, I just noticed this. Be careful on that component 1 that we already talked about. You do have to refer to plural concentrations because the concentration, right, is only the explanatory variable. Oh, I see what you're saying. Okay, so you have to refer to the four concentrations. Those are the treatments. If you just say the concentration of the spray, that's just the factor, that's just the explanatory variable.
So jotting down the actual measurements.
You don't even have to do the measurements, you just have to say the four different concentrations. Or list out the four concentrations. Either one of those would work. You just can't say the concentration of the spray is the treatment, because it's not, that's just the factor, the explanatory variable. Yeah. Raina?
If the question asked about what is explanatory variable, would the answer be use of fungus?
No, it'd be the concentrations of the concentration of the fungus.
More specific.
Well, yeah. So like, think about it this way: if the treatments are the four different concentrations, then where are we getting those four different concentrations from? The explanatory variable, the concentration of the bug spray. So it has to be the concentration of the bug spray. That is the factor, the explanatory variable. Okay, and then the number 3 was asking for a response variable.
Yeah.
So based on the concentration of the bug spray, what are we measuring?
How many died?
How many died or how many are
Alive.
stayed alive, right?
Yes.
Yeah.
I just put if they stay alive.
You just have to have one or the other, I believe. So to satisfy component 3, it must be clear that the response variable is being measured separately for each experimental unit. Okay, so if you only say the number of insects alive, that is not satisfying it. You have to say the number of insects alive in each container. Insects alive or number of insects alive. Oh, insects and alive is not a variable. Yeah. So the number of insects alive in each container.
Oh, well.
New notice, it does say right here, it can be satisfied providing a binary response, so whether the insect lived or died, right? So you could say live or died in that case. But you do have to include the response variable is measured per experimental unit, right? So the response variable is measured per experimental unit. Okay? Does part A make sense? Do we see those details? Okay. All right. From there, let's look at the next part. What was part B? Does the experiment have a control group? What you think? Before you even look at the response. Yes. Why?
Because the zero.
The zero. So when we say control group, yes, it's the zero. So what is kind of the defining mark of a control group? It's a baseline, so no what? Active treatments. Don't forget that. So when we say baseline, there's no active treatment, or it could be like an old medicine that was already being used, right? Or something to that effect. So either no active treatment, or it was what was already being used. Okay, so yes, because the 0 milliliters per liter had no active treatment. So what did the rubric have on there? Essentially correct if the response indicates there is a control group and justifies this claim by identifying the control group or by explaining there's a treatment which contains no fungus, right? So do notice right here, you can still get a partially correct even if you said no control group, because you're like, oh, there's 4 different treatments, but it is important to notice that that is a control group, right, because there's no fungus. If any way, though, you imply that that is not a treatment, so I guess that was a big issue that year, is where people were kind of saying that the 0 milliliters per liter was not a treatment. So one of the ways that they developed this rubric is some of the table leaders, the chief reader reads through student responses, identifies, well, they create an idealized response first. They read through a certain number of randomly selected, obviously randomly selected so it's not biased, but randomly selected responses, and then build a rubric off of that. So there must have been some issue that year with people implying that that was not a treatment. Okay, so hopefully we recognize there is a control group because there was one treatment that had no fungus, had no active treatment, or active ingredient. Please make sure when you do say that active ingredient though, Dixie, that you include the context of the no fungus, right? So don't just use generalized terms, include the context with that.
No, that's what I thought.
Yeah.
I would just say for this.
I was just saying, huh?
I would just say for this scenario.
There's no fungus?
Okay.
Right, yeah. So, I mean, you could say 0 milliliters per liter of fungus. You could just say there's no fungus as the active ingredient, things like that.
Do we need to include the word active?
No, I mean, just saying no fungus was there is enough, but I'm trying to go back to that defining characteristic is no active ingredient. Okay, C, so this is kind of what gave some of us some trouble. So describe how the treatments can be randomly assigned to the experimental units so that each treatment has the same number of units. Well, so first off, hopefully this makes things easier once we have the correct experimental units. So what are the correct experimental units? The containers, right? So having the correct experimental units would be good. So what do I need to do first?
Label.
So label
Identifier.
the containers. How? Label them
Uniquely. 1 to 20.
Unique identifier.
with unique numbers 1 to 20. Okay? So label the containers with unique numbers. I don't know why I had the word them in there. With unique numbers 1 to 20. Okay? Then
Generate 5.
Generate using
so
random.
generate 5 unique
Oh.
numbers,
From 20.
from 1 to 20, right? So you do have to say 1 to 20 because you could say other numbers. You have to tie it back into the numbers you already said. So 5 unique numbers from 1 to 20
Using our random number generator.
using a random number generator. Then what?
And assign
Assign
the
those to
containers,
zero.
Assign those
5 containers
to,
to 1.2, I don't know.
Does it matter
about
what you
what
like?
it does not matter. Yeah, so it doesn't matter the order. You just pick one. But you do need to generate 5 unique numbers. You assign those to 0 milliliters per liter fungus mixture. Then repeat with 5 more unique numbers. Yeah. I will say, I think we'll check, but I think saying repeat is enough. Repeat with 5 more unique numbers. I have to say this so it's clear that I don't get any of the previous 5. Okay? So 5 more unique numbers, 1 to 20. Assign these to 1.25 milliliters per liter.
Is it?
And then repeat for the last 2 treatments. So we'll see what they actually put in the rubric. But notice you have to randomly generate 5 unique numbers, assign them to 1 treatment, randomly generate 5 more unique numbers, assign them to the second treatment. Andrew, what you got?
Do they do consistency points on APs and stats? Like if we were to get the experimental units from all and then reuse?
Yes. Yes, yeah. I was going to show that to you in the rubric, but yeah, if you look at the rubric, so if you get the experimental units here incorrect, but you apply those experimental units down here, they read with your mistakes, okay? And that's actually a really important part for when we get to like stuff like probability or the inferential statistics. I don't care what happens in part A or B, put something down so that you can use it in parts B, C, and D, right? So if you have no clue on A, put something down and use that, because you might be able to use it later, right? So you can make mistakes and they'll read with your mistakes, right? So, Ian and then Randall.
Okay, for the rest of the parts, do you have to keep writing out for the other mixtures?
Let's find out. And Randall, what was your question?
Is it fine to say unique identifiers instead of unique numbers? Or
Yeah, unique identifiers, those are your numbers. Okay, so I'm going to show you, by the way, that there are lots of different ways that they do the random assignment process. I use the random number generator because it's the most straightforward, okay? But it creates appropriate levels for or labels for the units or treatments. So label the containers 1 through 20, label 20 slips of paper with 5 for each treatment, something like that. You have to correctly implement the random assignment process, and then the random assignment process has to result in equal number of experimental units to each treatment. Okay? And by doing 5 unique numbers and then 5 more unique numbers, you're guaranteeing that each treatment gets 5 applications, right? By the way, what are we going to call that, the fact that we have 5 of each treatment? Replication. So don't forget, right? Like that's one of those big tenets of experimental design, or elements of an experiment. You need replication at play. All right, so let's look and see what they said. If the response states that the insects are the experimental units in part A, the response in part C can be in terms of insects or containers, right? So that's that question you were asking, Andrew, right? In either case, the same 3 components are used to determine the score. Let's see. Yeah, so do notice though, like if you say containers in A, but you talk about insects in C, then those are not saying the same thing, so you don't get component 1 there. Okay, so they explain all these different ways to do slips of paper. Let's look, and so you have that. I didn't print this part out, I probably should have. Notice, you can do it with a random number generator or a 20-sided die. Who doesn't love? Yeah. Huh? Yeah, like, that's like one of the most like, D20 is, yeah, D20 is like the most important die in a Dungeons and Dragons game, for sure. It determines like everything. All the other dice are determine like damage and things like that, but a D20 determines if you're successful in something, determines if you get an attack in, yes. And it's been a hot minute since I played because we got a 2-year-old and we don't have time for that. You gotta like pay a babysitter. Yeah, with a few of our friends, yeah. Yeah. One of our friends that we play with or used to play with is Mr. Reed, if y'all remember him from last year.
Oh, I forgot him.
Yeah. So anyways, coming back up to here, if the initial assignment of numbers to units does not give each unit the same probability, that's not what I care about. Here we go. If the response does not indicate that the numbers are selected without replacement, or that different numbers must be used, the response does not satisfy component 2. So notice 5 unique numbers, and notice that's why I said 5 more unique numbers. So you can't just say 5 unique numbers, it's got to be 5 more unique numbers, things like that. So notice there's a lot of different ways to make this work. I will point out, so one of the things to be careful of right here, if you only assign them to a group, but you don't then assign them to a treatment, so you could say, generate 5 unique numbers to form one group, generate 5 more unique numbers to create a second group, but you don't actually give it those treatments, you're not getting full credit, you have to assign treatments. Thought there was something there. So it doesn't actually clarify if you have to go piece by piece, but I would probably do this, repeat this process for the next group and assign them the 2.5 milliliters per liter, and then the rest of the containers get the 3.75 milliliters per liter. So yeah, you don't have to do all that, but they do give you space. I will remind you, how many minutes did you have to do just this one question? 13, right? So like, could you take the time to write all this out?
Yeah. Oh, yeah.
You do, right? And it's 13 minutes on average. Some questions do take longer than others. Experimental design, because of the procedural nature of it, what I mean by that is it's the same question almost every time. It's either random selection and about bias, or it's about random assignment and confounding and maybe causation versus correlation, things like that. But that's what it's always about, so it's pretty straightforward in that regard. All right, any questions about this one before I go over some of the AP classroom questions?
Should we compare the results with the last one?
For that question, no. Because what does it say? It just says,
How treatments can be assigned.
right, it just says how can the treatments be randomly assigned. It does not ask you what to do at the end. Should you compare the results at the end? Yes, but that's not what the question asks. Okay, so I grabbed some of the questions that were some of the more highly missed ones. If only 1 or 2 people missed it, I didn't grab it. I'm going to move through some of these a little bit quicker. Some, a lot of us missed, so we need to go over it. So in this one, we have some new formulas, right? And what they hope to know is if customers will like them even more than the original formula. They, what was it, sample of 50 customers. Why is a sample of 50 customers important?
That's replication.
Replication, okay. Each customer takes both formula A and formula B in a randomly assigned order. So why are they saying it like that? Well, first of all, I do want to point out you're blocking on the individual, because could a person is one person's taste buds more similar to another person or more similar to themselves? Themselves. But if you gave everybody formula A first and then formula B first, there is a confounding element. So they randomly assigned some people to have A first, then they would have B, or they would have B first and then A, right? Which of the following best describes this study? So, was there replication?
Yes.
Yes. Because there was 50 customers, there were 50 experimental units that it was applied to, right? So it's not about customers tasting formula only once, there was replication in experimental units. The study is not well designed because formulas A and B are not compared with the original formula.
Correct.
That is correct. right? There is a baseline that we want to compare against. If I only try A and B, how do I know if I like it better than the original? So that's the problem. Okay. Do we care about a random sample here?
No, because it's an experiment.
It's an experiment. We didn't want to generalize to a population. We just wanted to determine cause and effect, the type of formula causing preference. We just talked about D actually, kind of gave that one away. And is 50 enough replication?
Yeah.
Kind of. I mean, it depends. We'll talk more about how high of a replication you want in a later unit. We don't know that right now. As long as there's replication, you're good. That question makes sense?
Yes, sir.
Okay. Number 3, I think this is a higher miss one for sure. Diane wanted to demonstrate which pruning technique was best for controlling the growth of certain types of shrubs. So she selected 10 shrubs of the same type, randomly assigned each one to receive 1 of 10 different pruning methods. What's the problem right there? She only has one. Actually, I will say this. It actually might be important that she only has one type of shrub. Why?
Because there's no.
So if we have different types of shrubs, that could be a confounding variable. Because do we care about the types of shrubs? No, what do we care about?
The pruning method.
The pruning technique. Now, we wouldn't be able to generalize to every type of shrub. We could only apply it to that type of shrub. So that's important, right? But that would allow us to directly control the confounding variable of the type of shrub. But what's the problem with she has 10 shrubs and randomly assigns each one to a different pruning method?
You know, it gets only one.
No, each experimentally, or each treatment is only applied to one experimental unit. If you don't use that treatment on more than one experimental unit, that's a problem. Yes, Kenzie?
Okay, like, I was like really confused on this one. So like, all of the 10 shrubs have to receive all of the 10 different pruning.
No. So she has 10 shrubs and randomly assigned each shrub to receive one pruning method. So this shrub only gets one pruning method.
Yeah.
This shrub only gets one pruning method. Is that not answering your question?
No,
What's your question then?
like, cause I was confused, like you just said like one gets one gets one. Like does one shrub get all 10 of them or no?
No, that's what I'm
Or
saying.
is it like
One
five?
shrub only gets one pruning technique.
Okay.
That's it.
Uh-huh.
And then the second shrub gets a different pruning technique.
Yeah.
And then a third shrub gets a third pruning technique. So we only use the pruning technique on one shrub each time. So realistically, we should have that treatment, the pruning technique, used on multiple shrubs.
So like the same shrub technique for each.
I get what you're saying.
So,
it's C.
let's say, yeah, there's no replication. So look,
So do you mean like the
It would
same
be better
shrub,
if there
but
were
like
20
one and one
shrubs,
getting
yeah.
that same one treatment?
let me do this. Technique 1 should be applied to 1, 2, 3 shrubs. Technique 2, this would be replication, okay? And technique 2, and how many treatments do we have? 10, right? So I would need how many shrubs if I were to apply technique 1 to 3 shrubs, technique 2 to 3 shrubs? I would need 30, right? But how many shrubs do I have? I only have 10, so I don't have replication. I only have technique 1 on 1 shrub. I have technique 2 on only 1 shrub.
Oh, okay.
Does that answer that question? Dixie, does that answer your question? Okay. So the issue was each pruning method was used on only one shrub, meaning we did not replicate that treatment. We needed those treatments applied to multiple experimental units. That was like in the insect case that we just looked at. Each fungus mixture was applied to 5 different containers, 5 experimental units. Here, that treatment's only on 1 experimental unit. Yes, Raina?
So what I was confused with number C and D. What is the significant difference between two of them?
Well, I would never do D. I'm not going to use 10 different treatments on 1 experimental unit.
Oh.
Unless it's like a magic hairs or something like that, but no. I'm not going to use lots of treatments on a single experimental unit, okay? All right, question 6. This, yes, what you got, Sophie?
So, in every experiment, it has to have replication for it to be well designed? Or?
Yes. Yes. Because here's the thing, okay, let's say it this way. Could it be that you had a fluke if you just applied it to one experimental unit?
Yeah.
Yes. But if you apply it to 100 experimental units and you get the same results, do you think it was a fluke? Probably not. The higher the replication, the more, it's called, so we talked about sampling variability, and so different samples get different results, but if I increase my sample size, that sampling variability is reduced. And so it's less likely a fluke and more likely that it's what the actual value is. So we're going to talk more about that, but yes, you always want multiple, you want replication. Okay. Experimental experiment, compare the adhesion of 2 types of paint, A and B, to 3 types of metals, 1, 2, and 3, used in automobiles. So first off, this is an experiment. And I want to go ahead and stop and point this out. How many, so what are our factors? The type of paint and the type of metal. Those are factors, okay? And the reason I'm bringing this up is because I want us to understand factors, levels, and treatments better. So here's factor 1, type of paint, factor 2, type of metal. Within the type of paint, what are the levels? A and B. Within the types of metal, what are the levels? 1, 2, and 3. So then what are the treatments? So A paint with metal 1, A paint with level 2, A paint with metal 3. B paint with metal 1, 2, and yeah, that's it. Okay. So how many treatments do we have?
I mean, 6.
6 treatments.
Alright.
Okay, so I hope that helps explain factor versus level versus treatment. If you only have one factor, your levels are your treatments. But when you have multiple factors, you have levels for each factor, and then you have to combine them to get the treatments. Okay, so paint A with metal 1, paint A with metal 2. Okay. We have 30 sheets of metal, 10 of 1, 10 of 2, 10 of 3. Half of each metal type will receive paint A, other half B. Adhesion of the paints. How many experimental units are there?
30.
There are 30 individuals that have the treatments applied. Okay? 30 individuals that have the treatments applied. Yes?
Okay, so like, can you explain again why paint isn't an experimental unit?
So the experimental unit is the individual that the treatment is applied to. So the paint is a factor. That's an explanatory variable. Remember, we're trying to explain the adhesion of the paints. That's my response variable. The paint is explaining the adhesion. The type of metal is explaining the adhesion. Those are my 2 factors. The units are the actual metal that is being applied to. The 10 pieces of metal. Or 30 pieces of metal, sorry. Okay. Does that answer your question?
Yeah, so both paint and metal are explanatory variables.
And we're also called factors. Each of those factors has multiple levels. You combine all your levels to figure out how many treatments there are.
Thank you.
Yep. Alright. We gotta finish this for lunch so you can come back and take the DYU. Pottery School wants to study whether the glaze of stoneware bowls is affected by temperature. The study will use 3 different types of clay because glaze can affect different clay in different ways. 8 bowls will be made with each clay type for a total of 24 bowls, and 4 different temperatures will be used. What is the best design? Now, just starting right away, should it be completely randomized or should it be blocked?
Block.
Okay, why would we want to block?
Because there are homogeneous groups.
So,
Possible homogeneous
the
groups.
types of clay glaze can affect different clay in different ways. So we get homogeneous groups that way, right? But the glaze, it could be a confounding variable. Because what do we actually care about?
The temperature.
So the glaze is affected by the temperature. So different clay is, oh yeah, so we want to know temperature is my independent variable, right, my factor, and how it is affecting the glaze. But clay, right, is a potentially confounding variable. It's related to both. It can explain the glaze, so we got a block on that, right? So completely randomized design is out. We're down to blocking. And then, did anyone get distracted by the matched pairs design?
Maybe.
Maybe? Okay, you cross it out? Okay. So the explanation that they gave in the book, and I think that, or in the AP classroom, and I think it's a good note, in a matched pairs design, you can only have 2 treatments. Because how many experimental units do you really have? 2. In a matched pairs, you have a pair, so it is 2. So you can only do matched pairs when you have 2 treatments. But how many treatments do we have here? 4. 4 different temperatures. So we needed a randomized block design and 2 bowls of each clay type. Notice, I think the 2 bowls is what got some of us, but what are the bowls?
The units.
Experimental units, but we have 4 different treatments, right? The 2 bowls, that'd be my replication. In a matched pairs, you have a pair, and then the pairs are replicated, right? So, yeah, that's the issue on that one. It is not a matched pairs design. We have too many treatments for that. Okay. Number 9, herbal medicine. We have some people with different injuries, and after the patients are on the medication for 2 weeks, the amount of pain reduction will be measured for each patient. Which of the following would be the best way to do a randomized block design? So what do we always block on? It is a potentially confounding variable. What we want to know is how the medicine is causing pain reduction, but what is a potentially confounding variable that we can block on?
Because people have different injuries.
Right. So different injuries hurt to a different level. So remember, I was just asking, what's the confounding variable that could be blocked upon? The knee injuries could be different from the arm injuries, could be different from the foot injuries. Okay? But a lot of foot injuries will be similar to each other. That's a homogeneous block. A lot of the arm injuries could be similar to each other. That's a homogeneous block. And so we're making these homogeneous blocks, and then remember, we're randomly assigning from within the block, right? So 12 foot injuries will get treatment A, 12 will get treatment B. 8 arm injuries will get treatment A, 8 will get treatment B. And finally, 20 and 20. So D?
Yes.
Yes. Okay. So hopefully that's explaining ideas. Well, a professor at a large university plans to conduct a study to compare the effect of online text versus regular printed text on student learning. If the findings are to be generalized to all students, which of the following must be part of the design? So, what is the researcher actually looking for? So, if we see that word effect, we should think causation or cause and effect. So it's got to be an experiment, it's got to have treatments, but what does this part ask?
Generalized.
Generalized to all students, so generalized to a population. What do we have to do to be able to generalize to all students?
We need a random sample.
We need a random sample. So D.
Yeah, I did not get that.
So in this one, they're trying to generalize for cause and effect, make an inference for cause and effect, but they also want to generalize to all students. So they have to have a random sample first, and then randomly apply the treatments. If you ever want to generalize to the population, you got to have a random sample. I haven't read all these, so I think that's the right one.
I think I got distracted by let's see.
I will point out D,
Yeah, I got D.
but here's the thing, if you have D, that's a census. You don't have to generalize to a population. If you pick D, you have a census, you don't have to generalize to a population. If you want to generalize to a population, you need a random sample. Okay? So yeah, I get why D might distract, but you don't have to generalize if it's a census.
I got it.
Nope. I don't know how to say that one otherwise. Nope. Alright, last one, and then we'll go to lunch and then come back and do our DYU. The owner of a plant nursery will conduct a study to investigate whether a new fertilizer is more effective than an older fertilizer in helping the growth of young tomato seedlings. The owner selects a simple random sample of 50 from all the young tomato seedlings in the nursery. Half of the selected seedlings were randomly assigned to receive the new fertilizer, remaining will receive the old. The growth of the seedlings will be recorded. What is the main reason why we select a simple random sample? What is the point of a simple random sample?
To generalize the population.
To generalize the population. So that would be D. Remember, what is there for establishing a causal
An
relationship?
experiment.
Well,
Wait.
what do you need? Yes, you need an experiment.
Oh, a treatment.
Yes, but what do you gotta do with that treatment?
Randomly assigned.
Randomly assign.
Oh.
So notice this question was trying to get you to notice random sample versus randomly assigned.
Yeah, so
This would be about random assignment. This is random sample.
I put B.
Okay? If you don't need your FRQ model while you're at lunch to study, if you want to hand it to me, I'll go ahead and start giving feedback on it. Just one less thing I'll have to do. It looks like better FRQ models than last time, so that's good news.
Wait, did y'all add
Yep.
more to the? Are we supposed to add more to this?
Before the test.
I've forgotten about making all
Today's, the test is
Well, the
Monday.
corrections, yes, test is Monday. The corrections before the test, I just needed the experiment size. Yeah, that's why I give you feedback, so that you can improve.
I didn't know to rank.
Corrections are before the test.
So I have until Monday.
You got time. When I handed that back, I told you about it. Or do you want it to study for the test, for the DYU?
No.
If you're not going to use it during, then give it to me. Do you want to add more to it?
Ian,
Is it not good?
I don't know, you're being weird about it. Yes.
It was good.
So,
Yes.
why do you not, like, choose a random sample?
It's not that you don't choose a random sample, but remember, a random sample is to reduce bias so you can generalize to a population, okay? But in an experiment, you're not necessarily trying to generalize to a population. If you can do a random sample before an experiment, then you can also generalize to a population. But remember, experiments are all about cause and effect. So we really worry about random assignment in an experiment to reduce effect. And the real reason why is because a lot of experiments, you can't randomly sample. If I am testing out medications to prevent cancer, I can't randomly sample from the population, I need volunteers. Because it'd be unethical to give someone medicine when they don't want it. So most of the time in an experiment, we can't do random sampling because of ethical concerns.
actually,
And so because of that, we
Take
worry
this if
more
y'all are
about
gone and go to
causation
the
than
bathroom
we
and
do
I don't
about
care. Take this.
random sampling. So if you could do random sampling
Don't have one
in an
more to do while
experiment,
you're
awesome.
waiting.
Well, hey, I did better on
Because
this.
then you could generalize to a
Don't
population.
do that.
Does that make
I wanna
sense?
be here.
Yeah. So it's more that we just usually can't.
Okay.
If you can, fantastic.
Alright.
Thank you. Wait, why
I
don't
gave
you-
you the extra one. I worked it, I
Right,
did the extra one.
I needed experiments. We're doing experiments one today. Our DYU's on experiments. You're supposed to do corrections before the test.
Oh!
So, yes, quickly, because I need to heat my stuff up as well. So Phoebe, work on that tonight. Since we're going to be a little crunched for time, because some of us are not going to be here Friday or leaving very quickly on Friday. We're going to go ahead and go over, one of the pens, it's just better to write with. We're going to go ahead and go over some of these, make the notes you need to improve it. If that yellow pen doesn't work well, let me know. By the way, a lot of these will have the little rubbery plastic pieces on the tip, so you may have to take that off. But yeah, let me know if the yellow doesn't work well. I have others. Okay. Okay. So number one, what was the issue in the in the false statement there?
Blocking reduces the effects of potential compounds.
Right. So it reduces the effects of potential confounds, not bias. Remember, bias is what we worry about in observational studies, not experiments. So make sure that you have that correct. So it's all about confounding. Yes, you probably need your, yep, DYU guy. Thanks, Charlie. Okay, number 2, a placebo is similar in appearance to the treatment of interest. Contains no active ingredients, but it does not have to be identical to the treatment of interest. It does have to be identical, otherwise you would know, right? So it has to be identical to the treatment of interest. So the first half of that's completely correct, but it does have to be identical to the treatment of interest. The first one is the effects of confounding. Yep.
What was the meaning of treatment of interest again?
I mean, it's just what the treatment that you're interested in. Yeah. Number 3, a study is an observational study if the investigator observes the behavior or response variable when one or more factors are manipulated. That's an experiment, right? That is not an observational study. If factors are being manipulated by the investigator, by the researcher, that is an experiment. Hopefully we're good there. Okay. Number 4, a factor is any particular combination of values for the explanatory variables. Treatment. Yeah.
These are low.
Remember, the explanatory variables are the what? Are the factors. When you combine the different levels of those explanatory variables, you're getting treatments, right? So a particular combination of values is a treatment. Okay, the levels are the different levels of a factor, but when you get to the combination of those values, you're getting treatments. So treatment is any particular combination. Okay. Number 5, random assignment to treatments will guarantee groups that are exactly alike for experimental purposes.
No, that's blocking.
It's not exactly like by randomizing it, we are reducing potential confounding.
Yeah, we're reducing potential confoundings, but like, does it guarantee they are exactly alike? No. They're relatively similar, right? So the random assignment, remember there's always the idea of sampling variability or randomness. So they're not necessarily going to be exactly alike, but we're going to filter out the effects of confounds by making the groups similar, not exactly alike. I mean, I would need a little bit more with that for an E, because like, it doesn't guarantee, well, it's more about the exactly alike. It will guarantee groups, or it'll ensure groups that are similar for experimental purposes. Yes, Andrew?
I didn't say something, but I said not exactly like.
I mean, that's true. I'll have to think on it, because the thing is, they're not going to be exactly alike, so you're not wrong, but really we need to recognize that they're going to be similar groups, right? Like, they're equivalent. Not exactly the same, but they're effectively the same, right? The whole idea is that we want similar. If they're just completely different, then I'm not going to be able to establish cause and effect very well, right? So it is all about them being similar enough. Any other questions through number 5 so far?
Oh.
Okay. Number 6, the method of reducing confounding wherein an extraneous variable is held constant is called blocking.
That's direct control.
That is direct control, right? When you keep an extraneous or an extra variable, and so I had to say extraneous, I guess I could have said potentially confounding variable. It's just reducing confounding wherein a potentially confounding variable is held constant. It feels awkward. Holding it constant is direct control. Yes, ma'am?
I just said control, I didn't say direct control.
That's fine. Just be careful on control versus control group. That's why I say direct control, so that there's no confusion with control group. Yes, Lorelai.
Well, you just answered my question, because I put control group.
Yeah, sorry. So remember, a control group is that baseline for comparison. Direct control is when you hold that variable constant for every experimental unit. Yeah. Raina.
What is, can you recap the meaning of direct control?
Direct control is when you hold a potentially confounding variable the same for every experimental unit. But you keep it exactly the same. So let's say that I'm looking at plant growth and I want to know how water affects how much a plant grows. Well, sunlight also affects how much it grows, but I don't care about that. So I give every plant exactly the same amount of sunlight every day. I directly control, keep that variable the same. All right. Number 7, a control group provides a baseline for comparison to a treatment group, and every experiment needs a control group.
No,
Not
not all
every
experiments.
Yeah, not all experiments need a control group. Okay? Every experiment needs what?
Treatment.
And comparison. But you don't always need a control group, okay? You have to have comparison, you don't have to have a control group for comparison, though. Okay? Number 8, if the subjects, as well as the person measuring the response, are unaware of the treatment assigned to the subject, single blinding is being used.
Double blinding.
That is double blinding, right? So if the subjects are unaware, that's single blinding. If the researcher is unaware, right, that's single blinding. But if you got both, that's double blind. Okay. Final one here, I think, right? Replicating in an experiment means the entire experiment needs to be redone multiple times by different researchers.
No.
What has to be done? The treatment has to be applied to multiple experimental units, right? So, when we say replication, we mean that treatment has to be applied to multiple experimental units. Yes, Phoebe?
Wait, so would it be wrong if I said treatment groups?
It's not the treatment group as much, so I would say probably a P, partially correct when I go to score it, but it is more about each experimental unit gets that treatment multiple, or that treatment is used on multiple experimental units, okay? Andrew and then Kinsey.
Oh, where was that treatment needs to be applied multiple times?
That's fine, but I will say, like, for the purposes of like the AP exam and to prepare better, be aware that the treatment needs to be applied to multiple experimental units to have that full idea. Yes, Kinsey?
I put replicating in an experiment means that the different treatments need to be redone multiple times in the same groups. I have no idea what I was trying to say.
I'd have to look at that a little bit more closely. That's a little dicey though. Ian?
I said there needs to be more experimental units if possible.
Not if possible, there needs to be, and it's about that treatment being applied, each treatment being applied multiple times to multiple experimental units, okay? Right now, then we gotta move forward.
I said replicating is used to reduce confounding variables, not be done a whole experiment by the researchers. It would be just incorrect for
I'm gonna have to look at that one a little bit. I don't know off the top of my head, just hearing it. Okay, let's look at number 10. A study in Kenya was undertaken to determine if a relationship existed between the water drainage and mosquito population in different areas of the city. Using GPS, the city was overlaid with a map containing 50 grid cells. 10 of the cells that contained standing water and 10 of the cells with good water drainage were randomly selected, and the mosquito population was estimated for each cell. Which type of study was conducted?
E.
E as in echo?
Yes.
Okay, an observational study. There were no what?
Treatment.
There were no treatments, but the response is the mosquito population. What was explaining the mosquito population?
The drainage.
The drainage, right? So drainage was explanatory, response was mosquito. Yes, Andrew?
So you can have like response and explanatory and observation.
Yeah, so don't forget, an observational study just cannot show causation. There's a correlation for sure. But if it was an experiment, then I could establish causation between the explanatory and the response. So good question. Yes, you can have explanatory and response in an observational study. Okay. Number 11, spelling is an important skill in the early years of formal schooling. 2 popular methods of spelling instruction are rainbow writing and retrieval practice. The rainbow writing method involves copying, spelling words in different colors, thus creating a rainbow effect. The retrieval practice method involves taking a sequence of practice quizzes, comparing spellings. An experiment will be conducted to determine which of these 2 methods is more effective. They'll be randomly assigned to the rainbow writing or retrieval practice. Because older children are expected to be better spellers than younger children, the researchers will block by age. Unfortunately, it will be impossible to implement double blinding in this study. Why? B.
B.
Yeah. Yes. B, as in boy. The children will know they use rainbow writing or practice retrieval.
Well, how, like, okay, so, like, I was wondering, because, like, how would they know?
Well, they're doing it.
Okay, but like,
They don't have to know the name of it, but they know what they're doing, right?
what if they don't know it was a rainbow?
Yeah, the name is not what's important. What they're actually doing is what's important. They're still gonna get the color scheme. They're still gonna get the rainbow.
They still know it's and we all know that.
Why would it not be echo?
They have to block
Yeah, I
by
got,
age.
Right, they do have to block by age, but
So how could they not know the age?
they're blocking by age. That
Because it's the statistician that reports.
I'm gonna have to. I mean, it just. I mean, the researcher can be blinded on the treatments, right?
The kids cannot.
Because that's not, but they're not measuring the ages. Like, we don't necessarily, they're measuring how well they do, right? The researcher doesn't have to be the one who assigns the treatments. It could be a third party that assigns the treatments, and the researcher just collects the data. But the kids know which method they're using, right? Like, you can't hide it from the kid. Even if they don't know the name, can't hide it from the kid. All right, we gotta do this last one really quickly, sorry. The last one, 3 butterfly populations were estimated for each side of the road. I think this was a matched pairs, if I remember correctly.
What?
Hold on. Yeah, one side of the road was randomly assigned to be mowed every 6 weeks, the other side was not mowed. That's 1/2 mile section. Those two, that part of the road is one experimental unit-ish, and then half the treatments on one side, half the treatments on the other. That's a match pairs, for sure. All right, please leave your DYUs, hand them to me. I will give a little bit more feedback before tomorrow.
This guy's the one out across. What? I love when that.
Make sure you hand it to me. Hand me your DYU. I will look at it a little bit more.
Wait, so
Go do it. Go. Two. Hey, and I'm not doing This is one of those nights I got you.
I couldn't understand like what it was stating, like